Okay, so here's the sequence of operations we came up with: -2 row 1 plus row 2, which clears the first column, and then 2 row 2 plus row 3, which clears the second column and puts it in echelon form. And then you guys have been doing back substitution, and what that looks like is solving the third equation. You get z equals -1/2, right? And then solving the second equation becomes -y minus 2 times -1/2 equals -4. And that's going to be here +1. So we do +1. We can subtract that from both sides. So I think we're going to get y equals 5. I've done the algebra right. Is that what you guys got? Okay, so then that's the second equation. Then the first equation is x plus 2 times 5 plus 3 times -1/2 equals 6. So that's going to give, well, there's going to be, so x equals 6 minus 10 is -4 plus 3/2, which equals -2 4s is 8/2 plus 3/2, which looks like -5/2. So if we do the fractions correctly, we have minus x equals -5/2, y equals 5, and z equals -1/2. And you guys likely, if we've, okay, just a comment that, yeah, so we'll show, there's an algebraic manipulation program we can also use that does fractions literally like this, so that you can, like if you do this with a calculator, you'd end up with decimals, right? But this algebraic manipulation program will solve fractions problems and leave them as fractions. So that makes it simple in case you get tired of doing fractions. I try to avoid fractions just because you don't have to worry about linear algebra and arithmetic. Okay, so how do we package the solution? Well, we would write the solution. There's only going to be one solution, and we package the solution by writing S equals -5/2, 5, and -1/2. So we've written the solution set as a set of vectors. Okay, so our first homework assignment, for example, will just be solving linear systems, and you'll go through and solve them and write them, the solutions as a set of vectors. So we're practicing what you're doing on that. Okay, well, there's usually the row combination operation is usually pretty powerful. And there's only a few occasions when you need to use a row swap, a swap, or a rescaling operation. Okay, so that's basically Gauss's method, and it works for any linear system. Let us now. Let me see. Let's look at one thing. There's a geometric connection here about the word linear. If I have like x plus y equals 2, that's a linear system. And we think of it as a linear system because you're probably familiar with, if I wrote this as y equals -x plus 2 by subtracting minus x, you put this and you think, okay, well, this is a line. If I graphed the points x, y in the plane, it would be a line with slope -1 and y-intercept 2, right? So it would look something like this. And so if I have two variables, the solution set is a line. Or if I have three variables, x plus y plus z equals 2. Well, it turns out that this equation only fixes one variable. It's going to turn out I'm going to have two variables, they're going to be free, they're going to be floating. So if I sort of, that's going to fill out a whole plane, right? And it takes a little while to see that if you have any equation with three variables and like this, any linear equation with three variables is going to be a plane. And then what if you had x plus y plus z plus w equals 2? Well, I can sort of visualize this. I can sort of say, okay, well, I could because I can write down x, y, and z, and I could say solve this for z or something and see that as x, y goes over. It would be hard to see, but I could still imagine that it was a plane in some fashion. Okay, but this one is, and now the crucial thing is, in some sense, the line and the plane are flat; they don't curve. And it turns out the same is true in this case. The solution set here is going to be a 3-space inside a 4-space, which is impossible to visualize. Okay, but we call it a hyperplane. And it has the feature that it's somehow flat. It doesn't curve in any, it's hard to imagine, but it's like the plane, you can imagine it doesn't have any crinkles or curves in it, and it doesn't like bend in any way. And the same thing is true. So for any linear equation, it's in some sense flat. It doesn't have any curves or bends in it. Now, a linear system then is going to be, like if I have a linear system, x plus 2y equals 4 and 3x plus 5y equals 7. Well, each one of these is a line, right? So let's imagine, well, if they're both true, if both these equations are true, that means I've found an x and a y that makes both equations true. If I was to graph each of these lines, the idea here is the point xy that makes both these equations true would be the intersection of the two lines, right? So it's going to turn out that the solution set of any linear system like this with two equations and two unknowns is going to look like geometrically either an intersection, or if the lines are parallel, there wouldn't be any solution, any intersection at all. It would be no. So this is like one solution. This is no solutions. And the other possibilities, they can be the same line. Now, this linear system is the one we've dealt with. We had one solution. This one would be like, let's see, x plus y equals 4, and say 2x plus 2y equals 9. Because if I did a row operation on this one, minus 2 row 1 plus row 2, this would go to x plus y equals 4, and minus 2x would give me 0, and minus 2y would give me 0. But over here, this would be minus 4 times minus 2 is 8. I have 1. And you can see the second equation here is basically 0 equals 1, which is a contradiction. So if you apply Gauss's method to a system where one of the equations is the same, you get a contradiction. That's how the fact that the two lines are the same, the fact that the two lines are parallel but not the same, shows up. You get a contradiction. So then when we write here for this kind of system, we'd write the solution set equals the set with no vectors, with no elements, right? So we say there's no solution, but we want to sort of a uniform way. Okay, we have a solution set with one solution. And this is the empty set, the set with no elements. And there's a special name for this. Okay, this is a name for the empty set. Some people, for some reason, like to put this. Well, this is a set that has one element, namely the sets can be elements of other sets. So here, this has no elements. This has one element. This is not the empty set. Okay, so you don't. Okay, so you can use this one for this one here. Now, what about the one with this one here? Well, this could be similar to this. Let's say I had x plus y equals 4 and 2x plus 2y equals 8. Well, this one then, you see, because each term is twice the other one. So if I do the same row operation, minus 2, row 1 plus row 2, I'm going to get x plus y equals 4, and then 0 equals 0. So here's the linear system. What happened was, this is really this equation in disguise. It's redundant, right? It doesn't give me any more information. And so this a 0 equals 0 equation of linear system means there's some redundancy. Okay. These are the only three possibilities for any linear system, no matter how many equations, no matter how many variables, either one solution, no solutions, or an infinite number of solutions. This one, you see, has an infinite number of solutions because x equals 4 minus y. Choose y to be any number. 4 minus that number is x. So we get an infinite number of solutions because you can see these lines overlay one another. So we have an infinite number of solutions. Those are the only three possibilities. There's no linear system that has, say, just two solutions. No matter how many variables you have, no matter how many equations you have. So this is sort of a pattern. And one of the goals we'll try to do is to see how that works, how we can understand that. Okay, so let's